My name is Amiel Marvin Lloyd P. Castro and I will be discussing the definition of Laplace transform. So we let f of t be a given function which is defined by t is greater than or equal to 0. If there exists a function f of s so that f of s is equal to the integral of e raised to negative s of t times f of t with respect to dt from 0 to infinity, then f of s is called the Laplace transform of f of t. So Laplace transformation is a powerful method of solving linear differential equations. It reduces the problem of solving differential equations into algebraic equations. So to get the Laplace transform of the given function f of t, multiply f of t by e raised to negative s of t and integrate with respect to t from 0 to infinity. In symbol, e raised to negative st multiplied by f of t with respect to dt from 0 to infinity.
Linear property. The linearity property, if a and b are constants, while f of t and g of t are functions of t, whose Laplace transform exists, therefore, the Laplace transform of a times a function of t, or rather f of t plus b times g of t is equal to a times Laplace transform of f of t plus b times the Laplace transform of g of t. This property can be easily extended to more than two functions as shown from the above proof. With the linearity property, Laplace transform can also be called the linear operator. I'm Erline de la Cruz and I'll be discussing the first shifting property. First is the definition. The definition is the Laplace transform of e raised to negative kt times a function of t is equal to the Laplace transform of f of t, replacing s with s plus k. So the Laplace transform of e raised to negative kt times a function of t is equal to a function of s plus k. First example, the Laplace transform of e raised to negative 60 times t squared. In this example, the e raised to negative kt is equivalent to e raised to negative 60, so k is equal to 6, and the function of t is equal to t squared. So the Laplace transform of t squared is 2 factorial over s raised to 2 plus 1, which is equivalent to 2 over s cubed. F of s is equal to 2 over s cubed, and the function of s plus k is equal to 2 over s plus 6 raised to 3. So the Laplace transform of e raised to negative 60 times t squared is equal to 2 over s plus 6 quantity cube. Example number 2 is the Laplace transform of 5 times e raised to 2t. E raised to negative kt is equal to e raised to 2t, so k is equal to negative 2, and the function of t is equal to 5. So the Laplace transform of 5 is equal to 5 over s. F of s is equal to 5 over s, and the function of s plus k is equal to 5 over s minus 2, which is the Laplace transform of 5 e raised to 2t.
My name is Rainbow Provo Ayong and I'm gonna be discussing the examples of first shifting property. The first example is the Laplace transform of t raised to 5 times e raised to negative 5t. So you're gonna get the function of t first, separating the e raised to negative 5t. And when when using the knowledge of Laplace transform, so the Laplace transform of t raised to 5 is 5 factorial over s raised to 6. Then from the first shifting property, you're gonna make s 2s plus k. You're gonna get k from the e raised to negative 5t. So by adding k to s, it will be 5 factorial over s plus k raised to 6. By simplifying, you will get the Laplace transform of t raised to 5 times e raised to negative 5t is equal to 120 over s plus 5 raised to 6. The second example is the Laplace transform of cos 8t times e raised to t. The function of t is equal to cos 8t. So you're gonna find the Laplace transform of it, getting 8 over s squared plus 8 squared. And applying the definition of Laplace of the first shifting property, you're gonna make s into s plus k, getting k from e raised to t. So by substituting, you will get 8 over s minus 1 quantity squared plus 64.
The following transforms of elementary functions are derived from the definition of Laplace transform and can now be used to solve for the Laplace of a function. Using the Laplace transforms of elementary functions, find the Laplace transforms of the following.
I'm Crizel C. Chen and I'll be discussing the elementary Laplace transform examples. First, the Laplace transform of 3e raised to 7t. Using the Laplace transform formula, e raised to 8t 1 is equal to 1 all over s minus 2. The Laplace transform of 3e raised to 7t will become 3 over s minus 7. Next, the Laplace transform of 3 sine 2 theta. Using the Laplace transform formula sine 80, the Laplace transform will become a over s squared plus a squared. So the Laplace transform of 3 sine 2t will become 6 all over s squared plus 4.
So we have Laplace transform of t times a function of t. Here we have the formula, which is Laplace transform of t times any function of t equals to the negative first derivative of the Laplace transform of f of t. And we have here the Laplace transform by definition equals f of s. And here, when we differentiate that f of s, we will resort to this equation right here. Here we have Leibniz rule that shows the partial differentiation with respect to t of the Laplace transform by definition of t times a function of t, which results to this equation right here of negative Laplace transform of t times any function of t. Here we have the main formulas, which is the first derivative of the Laplace transform equals to the negative Laplace transform of t times the function of t, and vice versa. Let's have examples. First example is Laplace transform of t times sine t, where f of t equals sine t. Now, applying the Laplace transform of sine t equals to 1 over s squared plus 1, and differentiating that, we will have negative 2s over the square of s squared plus 1, and multiplying by negative 1, we will resort to the final answer of 2s over the quantity of s squared plus 1 squared. Let's have another example. Here we have the Laplace transform of t times the function of 6e raised to 3t, where f of t is the 6e raised to 3t, and when we get the Laplace transform of this, we will have 6 over s minus 3, and differentiating that, we will have negative 6 over s minus 3 quantity squared. multiplying by -1, we will result to the final answer of the Laplace transform of t times 6e raised to 3t equals to 6 over s minus 3 quantity squared. Now that ends the lesson for Laplace transform of t times a function of t.
The Laplace transform of derivatives. The Laplace transform of derivatives is defined as the integral transformation of derivatives of a function in any order. This is very useful in deriving Laplace transform of some function and solving differential equations. The property of the Laplace transform of derivatives is given below. This is where n is the order of derivative. By integration by parts, we can furthermore emphasize the property. Below, you can see the Laplace transform of the first derivative. Now, these are the steps in finding the Laplace transform of derivatives. First is to determine the function. Take note that if there are many functions used in an equation, use linearity property of Laplace transform. Second is determine in what order should the function will be transformed. After determining that, tabulate the first two n minus 1 derivative of the function, where n is the order in which it will be transformed, and then substitute 0 to the variable of the function. Fourth step is to find the Laplace transform of the function. Last is to substitute the computed values to the Laplace transform of the derivative property. The Laplace transform of derivatives. For example, we are asked to find the Laplace transform of y triple prime of t, where y of t is equal to e raised to 2t. Having the function y of t equals to e 2t, we substitute 0 to t and we get 1 for y of o, or y of 0. After that, we get the first derivative of the function, which is 2e raised to 2t. Substituting 0 again to t, we get 2 for y prime of 0. After that, we get the second derivative of the function, which is 4e raised to 2t. Substituting 0 again, we now get 4 for y double prime of 0. After that, we can now get the Laplace transform of the function. The Laplace transform of e raised to 2t is equal to 1 over s minus 2. Having the Laplace transform of the function, we can now substitute the formula or the property of the transform of derivatives. Substituting it, we will now get s cubed all over s minus t minus quantity s squared plus 2s plus 4. Simplifying the equation, we now get s cubed all over s minus t minus s squared minus 2s and minus 4.
Okay, my name is Franz Jason Bale, and I will discuss Laplace transform. Inverse Laplace transform. We are going to be given transform f of s and ask what function did we have originally. As you will see, this can be more complicated and lengthy process than taking transform. In these cases, we say that we are finding the inverse Laplace transform of f of s and use the following notation. F of t equals to L raised to negative 1 f of s. The inverse Laplace transform for L f of t equals to f of s. The value of f of t is called the inverse Laplace transform of f of s. In symbol, L raised to negative 1 f of s equals to f of t, where L raised negative 1 is called the inverse Laplace transform of operator. So this is the table of inverse Laplace transform. Inverse Laplace transform example. Find the inverse Laplace transform of 5 over s minus 2 minus 4s over s squared plus 9. Solution. So first, we have to factor up the 5 from 5 over s minus 2 and 4s of ay factor out the 4 in 4s over s squared plus 9. Then using the table, we can see that s minus 2 is equals to e raised to negative 2t, a positive 2t, and raise the 3 in 4 l raised to negative 1 s over s squared plus 3 squared. So the 1 over s will be 1. Then the s over s squared plus 3 squared equals to cosine 3t. So the answer is the Laplace transform, the inverse Laplace transform of 5 over s minus 2 minus 4s s squared plus 9 equals to 5e raised to 2t minus 4 cos 3t. Yeah.
Hello, I'm Miljan D. Bernaldez, and the topic that I will discuss is the inverse Laplace transform. The problem was inverse Laplace of 2s plus 3 over s squared plus 1. To get this equation, we need to solve the linearity property first. It is Laplace of 2s over s squared plus 1 and plus 3 over s squared plus 1. And the next thing to do is to distribute la inverse Laplace of 2s over s squared plus 1 and the plus inverse Laplace of 3 over s squared plus 1. Next is 2 inverse Laplace of s over s squared plus 1 plus 3 inverse Laplace of 1 over s squared plus 1. Then apply the formula. 2 times cosine of t plus 3 sine of t.